Today, we shall start from methods of preparation of haloalkanes and haloarenes. First method is starting from alcohols. We can use different reagents to convert alcohols into haloalkanes. The first reagent we are going to consider is concentrated halogen acids. Here we start from alcohol. General formula is ROH. We treat it with concentrated halogen acid. The general formula is HX. X can be chloro group, bromo group, or iodo group, and definitely not fluoro group. In most of the cases, you need the catalyst zinc chloride. Product obtained is alkyl halide, represented by the general formula Rx. Water is the byproduct. Whether I need zinc chloride catalyst or not is decided by the nature of the alcohol that you consider. If I go for tertiary alcohol, it is the most reactive alcohol. Presence of zinc chloride is not required. So, with the tertiary alcohol, I need not make use of zinc chloride catalyst. In such cases, what we do, we simply shake tertiary alcohol with concentrated halogen acid at room temperature. Next point is, here, imagine in the first case, I'm going to fix HX. Like I'll fix it as, let us say, HCl. I can go on varying the nature of alcohol. What I mean is I can consider tertiary alcohol, secondary alcohol, or primary alcohol. What is the order of reactivity and why it is so? So in order to understand, let us just write the general formula of tertiary alcohol and primary alcohol. When I say tertiary alcohol, I have this is a tertiary alcohol. So in this case, you have three alkyl groups on the carbon atom carrying OH group. We know that these alkyl groups are plus I groups or electron releasing inductive groups. As a result, the electron density on the carbon atom increases. In turn, carbon atom tries to push the excess electron density towards more electronegative oxygen. Hence, this carbon-oxygen bond will be cleaved more readily. That is why among different classes of alcohols, tertiary alcohol is the most reactive towards HX. The second factor is steric factor. In case of tertiary alcohol, the carbon atom is surrounded by three bulkier alkyl groups. So this carbon tries to reduce the steric crowding. It can easily do so by pushing the OH group out of the molecule. So for a particular HX, the order of reactivity of different alcohols is tertiary greater than secondary greater than primary. In the second case, what we do is I'm going to fix one particular alcohol. Let us say I'll make use of C2H5OH and I'll go on varying HX. What I mean is I consider HI, HBr and HCl. As I move from chloro to bromo to iodo group, the size of the halogen atom increases. So bond length increases, bond strength decreases. So breaking the bond is the easiest in case of HI. That is why for a particular alcohol, the order of reactivity is HI is greater than HBr is greater than HCl. It can also be explained in terms of nucleophilic strength. Once this particular bond is broken, I get I minus ion. Same way here I will get Br minus and here it is Cl minus. So if I consider the nucleophilic strength, iodide ion is a stronger nucleophile compared to bromide, and bromide is a stronger nucleophile compared to chloride. That is why for a particular alcohol ROH, the order of reactivity of HX is HI greater than HBr is greater than HCl. And this method in which an alcohol is converted into alkyl halide using HX in presence of zinc chloride catalyst is called Groove's method. Now, let us go to prepare a particular alkyl chloride. For that, I'll start from alcohol, treat it with HCl in presence of zinc chloride. We get alkyl chloride RCl plus H2O. Generally in the examination, they will ask you a specific conversion. In order to show that, I'll start from ethanol, where R group is C2H5. It reacts with HCl in presence of zinc chloride, gives you chloroethane or ethyl chloride and water. Same way, they can ask you, how do you convert isopropyl alcohol or propane 2-ol into isopropyl chloride or 2-chloropropane? The equation is similar. You write the structure of propane 2-ol, treat it with HCl. In presence of zinc chloride, we get isopropyl chloride and water. Now, how do we actually carry out the reaction? This is not required examination point of view. What we can do is we can pass dry HCl gas through a solution of alcohol, or I can heat a solution of alcohol in concentrated aqueous HCl. Next, we will go to prepare alkyl bromide. For that, we will start from a mixture of sodium bromide and concentrated sulfuric acid. The purpose is to prepare HBr in the reaction mixture. We know concentrated sulfuric acid is a non-volatile acid. So this non-volatile acid H2SO4 displaces volatile acid HBr from its salt sodium bromide. When I compare the boiling points of H2SO4 and HBr, you know that H2SO4 has a higher boiling point compared to HBr. In other words, I can say H2SO4 is a non-volatile acid when compared to HBr. The principle is a non-volatile acid H2SO4 displaces a volatile acid HBr from its salt of HBr, that is NaBr. Whether we are going to get NaHSO4 or Na2SO4 depends upon the temperature employed. If the temperature is greater than 180 degrees Celsius, we get Na2SO4, and below 180 degrees Celsius, we get sodium bisulfate. Formation of Na2SO4 is not preferred because Na2SO4 forms a hard crust in the round bottomed flask that you have taken. and removal of that hard crust becomes very, very difficult. That's why we maintain temperature less than 180 degrees Celsius. So sodium bisulfate we will get. In the second step, formed HBr will react with alcohol to form alkyl bromide and water. Now, combining these two equations, we have to write the total equation. So, ROH plus sodium bromide plus concentrate sulfuric acid. You heat it, we get alkyl bromide along with sodium bisulfate and water. To write one specific example, I'll consider ethyl alcohol C2H5OH. When we heat it with a mixture of sodium bromide and concentrated sulfuric acid, we will get ethyl bromide, sodium bisulfate, and water. In presence of a mixture of sodium bromide and concentrated sulfuric acid, we can also make use of constant boiling 48% HBr. This constant boiling mixture is also called azeotropic mixture, about which you are going to study under solution chapter. Next, we will move over to study about preparation of alkyl iodide starting from alcohol. In this case, the reagent that we need is HI. This HI is generated by heating a mixture of sodium iodide or potassium iodide with 95% orthophosphoric acid H3PO4. We get alkyl iodide Ri and water. To write a specific example, we will consider ethanol C2H5OH. HI, how do we prepare it? Sodium iodide or potassium iodide with 95% H3PO4. You heat it, you get ethyl iodide and water. You can observe one important difference over here. While preparing bromide, I made use of a mixture of sodium bromide and concentrated sulfuric acid. When we come to the preparation of alkyl iodide, similar to NaBr, we have made use of either sodium iodide or potassium iodide, but in place of concentrated sulfuric acid, we have made use of 95% H3PO4. Now the question is, why should we replace concentrated sulfuric acid by 95% H3PO4? Now, in order to understand that, I'll consider the reaction. You have NaBr, where I heat it with concentrated sulfuric acid. We get sodium bisulfate and we get HBr. And we need HBr. But in the same way, if suppose I start from potassium iodide and H2SO4 concentrated, we get KHSO4 plus HI. Now, concentrated sulfuric acid is a non-volatile acid. That's why it displaces volatile acid HI from its salt Ki. But the problem with concentrated sulfuric acid is it's also a moderately powerful oxidizing agent. That's why it will oxidize formed HI to I2. Our aim is to get HI, but because concentrated sulfuric acid is a moderately powerful oxidizing agent, formed HI would undergo further oxidation to I2. And I2 is not a useful reagent in this particular reaction. That is why we have to replace H2SO4 which is a non-volatile oxidizing agent, by a non-volatile non-oxidizing agent. And the best example we can consider is H3PO4. Definitely H3PO4 displaces Hi from Ki, but because it is not an oxidizing agent, Hi will not get oxidized to I2. So this is one question generally asked in the examination. So that's what I have written over here. H2SO4 being a non-volatile acid displaces Hi from NaI or Ki. Being a moderately powerful oxidizing agent, H2SO4 oxidizes formed Hi to I2, but H3PO4 is non-volatile and non-oxidizing. That's why H3PO4 can produce Hi, but this Hi will not undergo oxidation to I2. So this is one very, very important question in the examination. From that, we will move over to preparation of haloalkanes starting from alcohols, but this time we are going to use phosphorus halides. When you say phosphorus halides, there are two possibilities. Either I can have pentahalide or I can have trihalide. First, I'll start from phosphorus pentachloride, PCl5. Start with alcohol. You have to heat it with PCl5. We get alkyl chloride, POCl3, and HCl. So what is the role of PCl5? It will replace the OH group by one chloro group. Then, whatever OH group is replaced, one hydrogen of OH will combine with one chlorine atom of PCl5 to form HCl. What I am left with here? PCl3, and that PCl3 will combine with oxygen to form phosphorus oxytrichloride. So, if I want to replace OH group by Cl group, one very important reagent that you can make use of is PCl5. What about the byproducts formed? POCl3 and HCl. So to write a specific example, I have considered ethanol with phosphorus pentachloride. We get ethyl chloride, POCl3 and HCl. But instead of making use of phosphorus pentachloride, I can go for trihalide also. When we say trihalides, we have only two trihalides that are readily available. One is either PCl3 or second one is PBr3. So when you consider PCl3, what way reaction takes place? In PCl3, whatever three chloro groups are there, they can replace three OH groups. That is why I will start from three molecules of alcohol. I heat it with phosphorus trichloride. The three OH groups present in three molecules of alcohol are replaced by three chloro groups. I get 3 moles of RCl. In addition to that, what we are left with? We are left with one phosphorus and three OH groups. So if I club it and write it, I can write as POH thrice, and POH thrice is same as H3PO3. Remember, when I make use of PCl3, the byproduct formed is H3PO3. It is also called orthophosphorus acid. In the same way, I can make use of PBr3. We get alkyl bromide along with the formation of orthophosphorus acid. Generally, PBr3 or Pi3 is obtained in situ we generate PBr3 and Pi3 in the reaction site, in the reaction mixture. How do we prepare it? We will consider a mixture of red phosphorus and we take it either with bromine when we want PBr3 or iodine when we want Pi3. So while writing the equation, we can write like this: 3 moles of ROH PX3. Here I told you X can either be bromo group or iodo group. These are prepared in situ by considering red phosphorus with bromine or iodine. We get 3 moles of alkyl bromide or alkyl iodide along with H3PO3. The third reagent that I can make use of is what is called thionyl chloride, and the corresponding process is called Darzens process. In Darzens process, we start from alcohol, ROH, and the specific reagent used here is thionyl chloride. Formula is SOCl2. This reaction is carried out in the presence of a weaker base like pyridine, and we have to reflux the reaction mixture. What happens? OH group is replaced by Cl group. I get RCl. Here you have SO will combine with one oxygen to form SO2, which is a gas. And then I'm left with one hydrogen and one chlorine. You get HCl, which is a gas. And this is a Darzens process. In this reaction, I use pyridine because just now I told you it is a weaker base. That's why it reacts with a stronger acid HCl to form the salt. As a result, concentration of the product keeps on decreasing, and according to Lee-Chatelier's principle, to compensate for the decrease in concentration of HCl, equilibrium shifts more towards the right, and this will favor higher yield of alkyl chloride. Now the question is, can I make use of this method to prepare a bromoalkane and iodoalkane? Answer is no. It is because to get bromoalkane, I have to make use of thionyl bromide, SOBr2. But the problem with SOBr2 is it's highly unstable and very, very expensive. Same way, to get iodoalkane, I have to go for thionyl iodide, SOI2. But what is the problem with SOI2? It does not exist at all. That's why Darzens process is used only to prepare chloroalkane, definitely not bromoalkane or iodoalkane. Now, one important question asked in the examination is, if suppose you are given an option of using either thionyl chloride or phosphorus pentachloride, which method is more useful? For that, just concentrate on the byproducts formed. Here, the byproducts are SO2 and HCl. Both of them are gases. So when you reflux it, as soon as they are formed, they will escape off, leaving behind pure chloroalkane. But when you make use of PCl5, HCl is gas, no doubt, it will easily escape off. But POCl3 is a colorless, transparent liquid which easily mixes with the liquid alkyl chloride. So separation is a difficult one, is a problem. So getting pure alkyl chloride is not so easy. That's why in between phosphorus pentachloride and thionyl chloride, I always prefer thionyl chloride to convert an alcohol into alkyl chloride. So that's what I have mentioned over here. Preferred method because byproducts HCl and SO2 being gases easily escape off, leaving behind pure alkyl chlorides. Now, next, we will start studying about preparation of haloalkanes starting from hydrocarbons. First reaction we are going to consider is by free radical chlorination or bromination. You have already studied about chlorination of methane in class 11 under hydrocarbon chapter. You have also studied the free radical substitution mechanism over there. It is the same thing. But what I have done, I have considered butane. The reagent for chlorination is Cl2, and for free radical chlorination or bromination, either I have to make use of UV light or I have to heat it. Now, you are going to get a mixture. If the hydrogen atom from CH3 group is replaced, I will get N-butyl chloride or 1-chlorobutane. On the other hand, if one hydrogen atom of CH2 is replaced, I am going to get 2-chlorobutane, or we call it as secondary butyl chloride. Now, what is the important demerit of this particular process? The first important demerit is you are going to get a complex mixture of isomeric mono or polyhaloalkanes. When I say that, in this case, I have considered only monochlorination. Reaction need not stop here. It can go for dichlorination, trichlorination, etc. Like that, polychlorination can take place. So first, you will get monochloroalkane. Then there we can have isomers, and this can continue for polyhaloalkanes. So we get a mixture of products, and whenever you get a mixture of products, what's the problem? It is difficult to separate them into pure compounds, and because so many compounds are formed in the mixture, what about the yield of one particular product? It is very, very less. That's why this free radical chlorination or bromination of hydrocarbon is not a convenient method to prepare haloalkanes. So there is one example question, example 10.3. Write all possible monochlorostructural isomers formed on free radical monochlorination of CH3 twice CH2 CH3. Now, to understand this clearly, I've written the structure of this molecule. So it is CH3, CH, CH3, CH2, CH3. This is actually called isopentane. Now, when you look at this isopentane, you can make out that there are 4 different types of hydrogen atoms. Which are the 4 different types of hydrogen atoms here? Imagine, if I replace one hydrogen from this CH3, I am going to get this compound. I'll get CH2Cl. In the second case, I'll replace one hydrogen atom of this CH2 group by chlorine. I'm going to get the second product where you have hydrogen atom is replaced by chlorine atom on the second carbon atom. Right? If I start from the right hand side. Then I can even replace this hydrogen by chlorine. Correspondingly, we get this molecule. And finally, I can replace one hydrogen from this CH3 group by chlorine. So what I get? I will get CH2Cl group. And this CH2Cl is definitely different from this. So how many products are obtained altogether? We will get 4 products.